When I switch to slides.
Oh, actually, do you want to share your screen just so that the people on Zoom can see
Oh,
your screen?
okay, turn on the screen sharing.
So, you were there. Yeah. Perfect. Awesome.
Okie doke. Welcome, Rafal Urbaniak. He obtained his PhD in philosophy from the University of Calgary. He's been British Academy Visiting Fellow and a Trinity College Longmoon Hub Visiting Fellow and a postdoctoral fellow of Research Foundation Flanders. Now he is an associate professor at the University of Gdansk, running a National Science Center project of legal probabilism. He is co-author of the Stanford Encyclopedia of Philosophy entry on legal probabilism. Rafal is interested in applications of formal, especially probabilities methods, to philosophical and social problems, such as those related to the legal applications of probabilistic methods, algorithmic fairness, and formal epistemology. He's been published in Logic and Logical Philosophy, Computers and Human Behavior, amongst his many publications, and Review of Symbolic Logic.
Thank you.
Please welcome Rafal to talk about taking
Cool.
seriously.
Can you guys hear me there? Can you see the slides?
Yes.
Yes. Okay, cool. Alicja, can you show yourself at least to say hi?
Yes, of course.
Uh,
Hi, everyone.
you're not pinned.
Oh, there you are.
Oh, there she is. Yeah, so this
Ah.
is Alicja. Whenever I say I by mistake, it's our joint work. So whenever I say I mean we, unless I say something stupid, in which case I am to be blamed. The last time Alicja gave this talk, so it's only fair I do it now, and it's more lively if I do it in person. But it is our joint work, and please, we'll try to torture her a bit in the Q&As. Let's get started, and please interrupt me if you need any clarification. I'll try to be gentle. Sorry, the subtitles kind of here cover the main thing. I'll try to be gentle. So the first part is really a kind of crash course in what embeddings are, and in how cosine similarity is supposed to work, how it is motivated. Then we go over what measures of bias people can pose for word embeddings, and then we go with our critical part, and our positive construction. So let's do this. So for some reason, it's nice to supposedly it's nice to be able to process language using computers. So one question that arises naturally is how to represent words with numbers, right? And well, one straightforward idea would be, hey, write down all the lexical units, give them numbers, and what you get is kind of one hot encoding, really, right? So basically, each word is one number, but that's not very exciting because that doesn't capture relations between words. That's not related to any data, it's just a list, right? You cannot do much with it. So here is a different idea. Let's use neural networks somehow to represent words with vectors. Now let's put aside the word parts aside, and let's focus on neural networks. How are they supposed to work? So that we have some idea of where this comes from. This guy's is so-called perceptron. It's one of the earliest. You might have seen this. If not, you didn't lose much, because now we're going to hear about it. It's like from the 50s, right? The idea is, hey, suppose we're devising something to recognize the digit 8, right? Handwritten in various forms. One thing you can do is you sort of pixelize the image, and then each pixel gets some number as a value, like intensity. Then you treat them as separate inputs. You throw it in. You take some weighted sum, and you get an output 0 or 1, whether the system recognizes it as a number, as this digit or not. Right? And now, wait, did we? Yeah. Okay, that's a problem. Yeah, like this. Yeah, that's better, sort of. The nice thing about it, supposedly, is that you can train this right? So basically, hey, let's start with some weights. Let's test it against some cases. And now every time you make an error, you sort of go back and revise the weights, and the most attention that you pay is to those weights that contributed to the error the most. Right? Basically, that's the idea. That's like backpropagation. And you can, of course, make it more complicated, right? Because like recognizing one digit is not very exciting. So how about you want to recognize all digits? Right? Then the way it's structured, well, you add a layer, but basically it works the same, right? You get like a bunch of numerical entries, one for each pixel. Each of those nodes treats them as input, right? Then weights them, gives some output, right? And then sends some activation to all these guys, right? And the most activated node, output node, is the guess, right? The most likely guess. And of course, you test it, right? You backpropagate. This is a bit more complicated, but basically, you try to change those weights that contribute to the error the most, and supposedly that way you teach the network to recognize digits. That's the basic idea. Now, what does that have to do with semantics and with words? There is this somehow vague philosophical / linguistic idea that some people would like to track back to Wittgenstein, but he's overrated, so we're not mentioning him in this talk, except for this time when we mentioned that we don't mention him. And the idea is, look, perhaps we can think of words or in representation of words in terms of what company they keep, right? Like words they co-occur with, particularly. So there's this intuition that, hey, similarity between words has something to do with how often people put them together in very narrow context. And the dream, kind of pipe dream really, is that once you represent those with vectors, then you don't really have to individualize lexical units, right? It seems like, take the word charm, right? In one sense, right, it seems sensible to connect it kind of along one dimension with wit and humor, right? But there's also a completely different direction, bracelet jewelry, right? And the idea and the hope is that once we think of words as vectors, the directions can be thought of as the representation of semantic relations. Yeah? Whether it works, we'll see. So how does that work for words? Basically, what you do is you train the network to optimize or to predict the words that are most likely to co-occur. Right? In the simplest approach, basically, what you're doing is you take pairs of words and you try to estimate how likely they are to occur, and you want to train the network to optimize for this. And and usually those networks have like 300 units. The idea is this: list all the words in your lexicon. Yeah, for instance, hamburger, right? Then this number becomes an input to a hidden layer of 300 nodes. They do the magic, right? And somehow they predict, so they send activation to output nodes, which are, again, as each of them is associated with a lexical unit. And the most activated unit is supposed to be the most likely, the word that's most likely to co-occur with the word hamburger, right? And now, how do you represent the word hamburger with a vector? Well, you just take those 300 numbers, right? And you get a 300-dimensional word vector for the word. So the idea is basically this. Take a neural network where you have 300 hidden nodes, train it to optimize for co-occurrence in one way or another. There are variants and bells and whistles, but this is the simplest kind of strategy. And you use those weights as the mathematical object representing that lexical unit. Okay. So you get words, you get them represented by a long vector. Now, how is this supposed to capture semantic relations? Yeah. So this is the first part of our puzzle. How words get represented as numbers in this framework. Now the question is, how do we represent relations between those words? And presumably, this is going to be, the mathematical counterpart is going to be relations between the vectors. What relations? Well, the general idea is you have to kind of think of vectors as being similar or not. So semantic similarity, at least that's the intuition, should correspond to how similar the vectors are. And what usually is meant by similarity in this context is the extent to which they agree in direction. Because length tends to vary with really seemingly unimportant factors. So usually what people do, they put aside the issue of how long the vectors are, it's just about the direction. What's the measure of that? Well, I'm glad you asked. Now some linear algebra, it's very easy. So let's start with this, right? You have, and okay, of course, I'm not going to go do drawings with 300 dimensions. We get 2, right? So start with 2 vectors, yeah? 1. And then you think of them as starting at the origin, and the numbers determine where they end, yeah? So think about these guys, right? 1, 2, 3, and 2.5, right? Easy, right? Nothing tricky. Now, one of the key notions here is the notion of a dot product. The dot product of 2 vectors, what you basically do is you take the numbers pointwise, right? You multiply them, and then you add all the results, right? And so the dot product of 2 vectors is not a vector, it's a number. And why the notion of dot product comes up? Because it not only connects to some things I will tell you about. One thing is that if you take the dot product of a vector with itself, right, it basically is the sum of its squared, shift in one axis and the shift in the other axis. You might have recognized it as something that if you take the square root, you get the length of A, right? So that's one natural kind of side effect of speaking of dot product, because if you take the square root of the dot product of a vector with itself, you get its length, in this context also called the norm of A. Okay? So far, so good? Another important element of this puzzle is also not very tricky, vector difference, right? Basically, to get the result of subtracting one vector from another, you subtract the numbers pointwise. So for instance, in this context, 3 minus 1, well, that's 2, right? So we are at 2, and 2.5 minus 2 is half, so we end up here. Unexciting, seemingly. Now, when you shift it, though, you get a triangle, and this is useful, actually. Because when you have a triangle, you can ask about the angle, right? And you can plug in trigonometry. And the nice thing about it is that you borrow this result for free from trigonometry. You play around with it, especially paying attention to the fact that squared norms are essentially dot products. And what you end up with is something like this. Right? So if you take the dot product, it's just the length of the one vector multiplied by the length of the other vector multiplied by the cosine of this angle. Right? So and the cosine of this angle is one way to represent the angle itself, right? So basically, when you talk about the angle and you want to talk about similarity, a nice way to do so is to use the cosine, right? Because, and why is it nice? Because if the angle is 0, right, the cosine is 1. So basically, what you do is, just simple manipulation, and you get the distance or the similarity between vectors. And now we're getting to the similarity bit. You just take the dot product, and if you want to normalize, some people do. In some contexts, you don't have to do this. You just multiply the lengths, and that's it. Right? So neural networks give you vector representation of words somehow optimized for frequency of co-occurrence, and then one simple trigonometric measure of similarity is the angle between those. The cosine similarity measure, and it's pretty easy. It's just dot product normalized by the result of multiplying the length product. So this is the conceptual kind of mathematical kind of stuff in the background. It's not very tricky. I just want us to be on the same page. Another nice feature of this is, hey, if being parallel is like as similar as it gets, then what's being natural? Well, it's being orthogonal. Yeah, and how, well, if you're being, what does it boil down to? What does this condition boil down to? Well, the cosine of 90 degrees is 0. So this needs to be 0. And since the lengths are non-null, this boils down to the dot product being null. Yeah, so now you have a clear, nice connection between the operation of taking the dot product and seeming semantic neutrality. Yeah, nice, right? So you seem to have like a scale that goes from that nicely. So if there's no connection, it seems to be 0. If the concepts are very similar, it's supposed to be close to 1. If they go in the opposite direction, it's supposed to be -1. Okay, and then some people talk about similarity. Some people talk about distance. Distance is from a scale on scale from 1 to 2. Neutrality is in the middle. Doesn't really matter. Just keep in mind that's the distinction. Okay, so what do those networks really learn? I'll give you an example because I have mixed feelings about how intuitive the results are, and I'm hoping once I give you this example, you will also have mixed feelings. Some suspicion. So take the word philosophy, yeah, and just a bunch of words and their similarity to this. So logic, yeah. Remember, it's on scale 0 to 1, yeah. So logic, okay, not terrible, 0.40 something, right? Nietzsche, Hegel around 0.3, but then Analytic and Russell and Continental are pretty close to Sandwich and Berger. Why? Well, hard to say, right? It's really the calculations are kind of not intuitive. But one problem is that people initially hoped that training of a network will help you isolate various meanings of a certain word. Right? So that, hey, Russell in philosophical context might mean the philosopher, Russell in other contexts might mean something else. Continental in the philosophical context might mean continental philosophy. In some other context, it might refer to continental breakfast or whatever. Yeah? This seems to have failed, and there are many examples like that. Now, interestingly, this is one of those networks. So to give you another flavor, another piece of what it looks like, say you take a word, then you take 10 top closest words. Now, in this particular case, the word, man and woman. And the only job-like words on those top 10 lists were robber for man and policewoman for women. What does that have to do with semantic relations? Not much, right? So it's kind of a reminder that it seems that there's something else that drives those similarity estimates, and that seems to be to have more to do with coherence than actually meaningful relations between those words. However, right, the problem is various tools use cosine similarity downstream. For instance, if you type stuff in a search box, autocompletion. So the worry might be, hey, if we train those networks on large corpora of text produced by humans, we know that humans have biases. Now, to what extent is it a threat for the way the semantic or coherence-like relationship are represented in the word embeddings? Right? That's the intuition. And the worry might be, it might be the case that stereotypically close words will end up cosine close to each other. That's supposedly the concern. Here is one example. It seems to be kind of typical in the discussion of that. Take some supposedly feminine occupations. Oh, also, by the way, for gender examples, we're using two directions. This is not because we think there should be two genders. It's because this is what has happened in the discipline. We're neutral with perspective that we're just playing along. Don't take this too seriously. So anyway, supposedly feminine occupations: homemaker, nurse, receptionist, librarian. Masculine occupations: maestro, captain, architect, boss. And when you look at unnormalized cosine distance, to he and she, it seems that seems to be some division going on that shouldn't be there in a fairly devised natural language processing tool. That's at least the intuition that people have. Okay. But now, how do you exactly measure the bias, right? How do you quantify it? That's the question. If you want to seriously approach this problem, you need to have a tool that measures it. You need to have a tool that helps to diminish the bias. And now, for that, you need to have some sensible measure of it. Here's one option that's very popular in the literature. It's called the word embedding association test. Here is the basic intuition, right? You start with two classes of, for weak, it's two. We will talk about more general setting in a minute. So suppose you have two classes of protected words, right? Here you have some male-related words, here you have some female-related words, whatever. And you have two sets of predicates. Yeah, one of them supposedly containing predicates that are stereotypically connected with one group, and the other with the other. How do you measure bias? Well, here is the idea. For instance, first of all, you assign S scores to particular words, right? So for instance, for he, what do? Well, you measure the similarity to predicates from one group. You take the average, right? So you're here. You measure the distances or similarities, depending on the context, in this context, similarities, to predicates from the other group. Take the average, so this is it, right? Then you subtract the averages, and you have the S score for this particular word. Okay? So you've averaged once so far. And you do it for each particular word. And now the weight score for these predicates given these classes is the average. Again, you take the average S score for this class, subtract from it the average S score from this class, right? And that's averaging the second time. Okay? And then you divide it by the standard deviation of all the S scores for all the words that you have. Should I repeat something? Is this clear conceptually? For each word, you look at the distance between the average distance to predicates here and the average distance to predicate there, subtract. Yeah, and then for each class, you take the average S scores. So it's you're averaging the second time. And to get the weight score, you subtract those averages and you kind of standardize by dividing by the standard deviation of the S scores. Okay. Now the official general formulation is like this, right? It looks sciencey. Is it? We'll see. But this is generally the setup. This is just like the formal version, the full formal version of what I just explained. It just applies to more. It's just supposed to apply in a more general setting. And people used it, well, to argue that bias is present. Also used it to study cultural changes throughout the centuries and whatnot. Interesting stuff, but methodologically suspicious, as you will see. Then what you do, and this is something. So the next question is, what do you do if you have more classes and more classes of predicates? Like religion, you have many religions. Race, you have many races. If it makes sense even to speak of, well, you know what I mean, right? Stereotypically, it seems that there should be more classes for some applications. Okay, so suppose you have, and this is the setup in used in the definition of the notion of mean average cosine similarity. The mean average is not an error. There is double averaging here as well. What happens is, take the word Muslim. Yeah? What you do is, first of all, you average the distance to predicates from the first class. You average the distance to the predicates from the second class. You average the distance to the predicates from the third class. And then you take the average, right? And crucially, to do statistical tests, you estimate p-value. They estimate. We shouldn't. No one should. But they estimate p-values by bootstrapping on the set of S-scores. This is important. It sounds tricky, but it kind of isn't, right? Because the key thing is here that they treat particular S-scores, which are results of pre-averaging, as raw data points. And then they apply classical statistical tests to those sets. Okay? The official definition is like this. Again, nothing exciting. It's just a general statement of what I just explained. Now, when you look at the data sets they use, right? So we downloaded the code, or Alicja did. When you look at this, it's kind of funny in the sense that they have protected words, right? But they are not grouped by religion. This is one weird thing. The second thing is they have predicate words, again, not grouped, and then you just have cosine distance or cosine similarity. And we'll say a bit more about this in a minute, but first, there are at least 3 directions in which this sort of methodology has been criticized. One is that, especially for wheat and so on, if you just compare and similar measures, if you just compare the similarities along one particular vector, like gender vector, and you try to improve on that, it seems, and the paper it's nice. I think the title is "Putting Lipstick on a Pig." What happens is, yes, you might get better score with respect to this particular vector, but it seems like the other relationship between predicates just gets transferred. So there might be areas where nothing really changes. Another idea is, hey, the standard criticism in the literature of this cosine measure approach is people use analogies, and it turns out that what analogies people end up listing is kind of funny because it's really parameter sensitive. And it seems there's some cherry picking in the examples that people have in publications. Then there's a really nice paper from just 2 years ago where it seems that there's some sensitivity to really weird factors, like, hey, let's throw in an animal name, kind of, or an animal species name, kind of, in there, or let's change capitals to lowercase, and the score changes, right? That's also raises some suspicions, but we'll put those worries aside. Another worry is that when you look at the word list they have, and you'll see some examples soon, it doesn't seem very principled. The words lists are pretty weird when you think about it. Then it seems that people haven't paid much attention to word list sizes. And there is this general paper which uses Bernstein bounds, saying, hey, look, if you actually, and Bernstein bounds are just those really, really wide skeptical theoretical bounds. And in this context, the application of the concept leads to the conclusion that, hey, you should have really huge data sets to even be able to claim bias. And that's kind of nice, right? Because someone finally pays attention to uncertainty, but it's also not very nice because the bounds are very theoretical, very wide, so they might put too much of requirements on the data sets. And then also Atanaya Raj said with his colleagues, gave a nice example showing in the generate case where you have 2 target words, we always give maximal value in either of the directions, which seems there is something conceptually off, right? And we're pushing in that direction as well. We show that there is something theoretically off, and it stems from pre-averaging, and it doesn't apply only in this limited extreme case, it applies everywhere. So the first thing is, right, and we were surprised no one came up with this, right? So how do you know if a certain distance to a group of words is a sign of bias? Well, compare this to the control group, right? What control group? Well, first of all, random words, but that might be not good enough, right? Also need some human-related predicates, right? Because it might be the case that certain words are closer just because they are predicates that are often mentioned in the context of speaking of humans. Right? So the proper control group here is human predicates, and which sort of we tried to end up with some that don't seem to carry much stereotypes. So we have this is our list of the beginning of our list of neutral words, and actually when you try to filter neutral words so that they don't seem to be related to stereotypes, lots of them get smashed, right? So, but anyway, so this is what we end up for, like for human-related words that do not seem to have race, religion, or gender connotations. So anyway, and then the third thing, well, the fourth thing is, and you'll see examples in a minute, when you actually look at the data sets, the situation is very uneven. So perhaps chasing a single number summary is not a good idea. To show you what I mean, here is what happens for the word Muslim with some randomly selected control words, right? So for the word Muslim, it seems, yes, that there seems to be some evidence of bias, right? The green ones are, because the other thing they didn't do is they didn't make a distinction between stereotype predicates that are connected to a given word and those that are connected to other words, to other groups, right? So for instance, in this context, so liberal and conservative in that word list was supposed to be connected to Christianity, right? This is a different stereotype. So green, same stereotype. Red, different stereotype. Blue, human predicates. Gray, neutral predicates. So in this context, what you get is, well, the stereotypical ones are kind of closer, right? Then you have a bunch of stereotypical predicates, but connected with different stereotypes. Then you have a mixture of human and neutral control words. Fine, okay? Yeah, that seems like, okay, maybe there is some bias here. But now take a look at priest, right? Priest, you start with human predicates, then you have different predicates from different stereotypes, then you have predicates associated seemingly on the list with Christianity. That's so weird, right? We started with such visualizations, and this got us thinking, hey, maybe there is much more variation than single-digit summaries, so single number summaries tell us. So, okay. Another issue is this, and this is a table that comes from the Mac paper. They took 3 different sets, right? Religion, race, gender. All the networks are trained on the Reddit corpus. And they looked at the Mac scores they calculated. And this is actually distances, not similarities. Sorry, this is distances, not similarities. So they're like, so mean average distance for religion is 0.85. That's just 0.14 away from 1, the neutral point. The score for race is very similar. The score for gender, okay, that differs a bit more. Right? But now the question is, okay, so, and then they try to improve on that, and the result of improvement is like, okay, there is some small shift, but it's not huge. The first question is, what grounds do you have even for thinking that this is a sign of bias? Right? I mean, think about it, right? That the first job word for men was robber, and it was like 0.55, right? So now the question is, what do differences that are so small, do they actually have any downstream effect in applications? Who knows, right? And secondly, they use p-values, and p-values are not good indicators of effect size. And because they are based on pre-average data, they are misleading, and we'll show this in a second. So what we will do in contrast is we will compare highest posterior density intervals, and I'll explain how it works in a second. Now, one reason to think that so look, here they said, okay, 0.85, that seems like a sign of bias. It's just only 0.14 from neutrality. Now the problem is, if you take neutral words or human words, only 56 or 55% in real databases is closer than this threshold, right? Around half of distribution for control groups already goes beyond this threshold that they took to be sign of bias, right? Suspicious. Similarly for race, right? For race, you get this longer tail, but still, right? Around a half of neutral or human predicates also are beyond this threshold that they relied on when reaching the conclusion that there is bias. Weird, right? For gender, this is actually a more clear-cut case. However, note that sure, right, predicates associated with male, for instance, seem to be closer to he, she, and such, but so do predicates associated theoretically with her and she. Yeah, so if is it a matter of co-occurrence, or is it a sign of bias, right? You would expect bias to be such that these guys move apart, not move together. Okay. Now let's move to pre-averaging. Why is it problematic? The problem is, if you build your z-scores or whatever you use in a classical test by dividing by standard deviation, that's not really the standard deviation of the raw data, but the standard deviation of the averages, right? You're dividing by a smaller number, so you're bound to get a higher result. Here's our example, or a bunch of our examples, and basically what we did is we assumed that distances have normal distribution with difference in mean 0. So we're going like this. Hey, suppose the generative model is such that there is no bias. Take the standard deviation of 0.8, which is pretty much what the standard deviation you see in real data sets. Question: what sort of bias scores would we expect to see then? If there is no bias, if you know that the underlying generating mechanism contains no bias, and you still can see high bias score, that means that something is off about that score, or that scoring method. So here's a very simple example. 4 terms, right? Term 1 and term 2 in one protected class, term 3 and term 4 in the other protected class. And for each, we draw 8 predicates from two predicate groups. We draw them from, again, the distributions where there is no difference. So in the generating mechanism, there is no difference. You should have the intuition that there is no major shift between the groups, right? And the means are very close. Do you have this intuition? Right? When you look at the picture, right, would you think that the picture itself tells you that there is a bias in one direction or the other between the red and the black? No. Yeah, they're pretty much, okay, they're a bit spread around, but the means are very close, and there seems to be no unevenness involved. What happens is, look, the standard deviation in the actual data is 0.07, but if you take a look at the standard deviation of means, it's 0.03. So when you divide by this, instead of dividing by this, right, you're going to end up thinking that the results are much more surprising than they really are. And even in the simple case, the weight score is 1.82, which is larger than the largest score reported in the original Kaliskan paper. You might think, okay, maybe this is because the size, the word list size is not realistic. Yeah, sure. If you run the same thing with the word list size of 8 protected words and 16 predicates per each, so this is again an example, like the same, right? The same assumption, no real difference, right? This is what the picture looks like. What's the real standard deviation? 0.08. What's the standard deviation of the means? 0.03. What's the weight score? 2 point something something, right? Very high, much higher than any weight score reported in any of the papers, and yet the generating mechanism, we know, contains no bias. And in fact, if you run this simulation for 10,000 times, this is the distribution of weight scores that you get. Yeah, they are kind of centered around 0, but 95% of the scores are between minus 2.7 and 2.7 on the right side, and 21% of the scores end up having absolute value higher than the highest value reported in the papers. Right? Okay, right. So the measure does have some connection to bias in the sense that if the difference is -1, it kind of shifts to the right. If the difference is 0.4, it also shifts to the right. But even if it's 0.4, the range is pretty wide. Yeah? So statistically, going this way and pre-averaging and running statistical tests and pre-average data is insane. So this is our critical message. What's the positive message? Well, let's think about the distances. Let's build Bayesian models that are supposed to capture the differences in a more sensible way. Here's our take on this. First of all, we use regularizing slightly skeptical priors, right? So we assume that distance is usually around 1, but I mean, there's lots of leeway. We assume that the standard deviation is not going to be that huge because, I mean, in fact, the usual standard deviation in data sets is around 0.8 or something. So that's very, very permissive prior. And the same for coefficients. We have very permissive prior on that. Just slight regularization. The models. Well, one thing is, this is the important line. One question to ask, hey, does it make a difference whether the connection is supposed to be to the same stereotype, to another stereotype, to a human predicate, or to a neutral word? What difference does that make? Well, it's not large. Those are 89% compatibility intervals. So it's like, take the posterior distribution, right? Take the narrowest interval that contains 89% of the mass. Where is it? First of all, the shift is really small. Right? Secondly, the uncertainty is pretty huge, right? You see that intervals don't depart from 0. And third, notice that the different and associated kind of seem to be moving together. You'll see more of this soon. So even if you take whole data sets that they have with our extra hundreds of data points added by adding control groups, what you get is, hey, there is no good reason to think that there is an important difference. Now, gender is a bit different. The gender data set is interesting because here you do have this difference, but instead of what you would expect, these guys moving in the opposite directions, they both move along, right? Which is, so is it a sign of bias or is it just a sign of the fact that people talk about gender and mention predicates applying to different genders in similar contexts, even though it's between the genders, right? So that makes you think that maybe cosine distances do not capture semantic relations. They might be much more focused on co-occurrence. Now, another interesting question, and this is kind of inspired by the fact that the shape of the the shape of the state of the distance, of what the distances look like for Muslim and for priest were so different that it maybe makes sense to look at it at a more fine-grained level. Groups of protected words, And here's what you get for religion, right? So again, here you have particular protected words, right? Here you have estimated distance, yeah? And now red are the predicates that are supposedly associated with a given word, stereotypically. Green are those that are associated with a different stereotype. Blue are predicates that are supposed to apply to humans. And gray are just like random words. Few things to notice, right? A few things to notice. One is that most of the time there is overlap between all of these, right? Secondly, even if not, there is no interesting or no strong overlap between different and associated. And in some contexts, even the different predicates seem closer than the supposedly associated ones. Muslim is actually one of the strongest cases you can make. And even for Muslim, given the size of the world those people are using, there is no sufficient evidence to claim bias. Gender. Gender is interesting because human predicates are much closer than neutral predicates, so that you see that difference. And secondly, the different and associated predicates are even closer. However, they usually overlap, right? And sometimes they overlap in weird directions, right? So here you have the different predicates closer than the supposedly associated predicates, and so on. So this suggests that first of all, the word list sizes are too small. But secondly, that even if they were bigger, the part of those proximity difference results that you get might be not due to bias. They might be due to the fact that predicates from various stereotypes get discussed quite often together. So they co-occur together. So whatever device you use to optimize for co-occurrence will end up having all of them closer to the supposedly protected word. Race is also interesting because in some cases you don't have much difference, right? That's one issue. And in some cases you do have, so black is a distinctive case because you do have a difference, and it seems you have good evidence, all probably better than Muslim. But for many other words, not really. Yeah, and in some of those, the directions go, the direction that things go is different from what you would expect, right? Here, for instance, again, the same thing, right? Different predicates from different stereotypes are closer than predicates from supposedly the appropriate, the corresponding predicate stereotype. So the bottom line, the existing measures simplify by pre-averaging that leads to false confidence. Secondly, we use simulations to show why this is way too hasty. It is way too hasty to use those measures. Third, we do run the Bayesian analysis, and a word lists are too short, and some of the results undermine the semantic interpretation of cosine similarity, and perhaps the fine-grained analysis shows that you should be very careful when you choose the words to use, and that the situation, just because your score is such and such, it doesn't mean that different protected classes are treated in an equally biased manner. And this is it, folks. However, this is unusual, but I would really like for you guys to spend a minute to fill an online feedback form. Please do so. We try to make it as clear and as presentable as we can. It would be very helpful to spend a minute just going to this link and just, saying, no, it sucked, or something like that.
It was to the presentation, not that no one sucked.
Thank you.
All right, question.
I have to go in 9 minutes, so
Why
I
don't you start?
have to talk to someone soon, so I have to leave for Q&A. But I have a question.
Yes.
I just want to quickly apologize and run off. So it seems like I lost the intuition for the measure, for like why one would think this is a good measure at all pretty early. And so I'm very happy to accept that it is not a good measure for all the reasons that you put forward. And it sounds like you have a pretty, I don't know the technicalities. I think you presented them extremely clearly, as clear as I could ever get them. But I'm happy with the diagnosis about pre-averaging being part of what's wrong. But I guess I wanted to hear more about the motivation for thinking that co-occurrence of words is adequate kind of basis for determining how biased, I guess. I guess I'm a little bit unclear about when people are using these tools, what sort of, how strong are the claims are they drawing from the measures that there exists hate speech, or there exists bias, or there exists mere association and we should look into it further? Like, do they make claims about the meanings of words?
There is a whole array of views. So those who are not critical. So what's the motivation? First of all, the motivation seems to be hey, there's lots of like cases where searching stuff on Google leads you to results that seem biased, yeah, or automated CV kind of selection methods end up with bias, stuff like that. So there are known clear-cut cases of bias somewhere downstream, right? It would be nice to be able to track it somehow to something that we can do something about. And many of these devices, if they use natural language processing, have some word embedding in the background, right? And what it usually does is it basically looks up the most similar words, right, or something like that. So the motivation is, hey, we have clear-cut cases of bias and weird results downstream. Perhaps we should track them back to something happening at the level of semantic of the representation of the language itself. One of the more used tools is word embeddings, so we should look at that. So what is used there? Well, cosine similarity. So let's pay attention to cosine similarity. Right? That's the motivation for thinking of cosine similarity in this context. And then when you look at early papers, well, computer scientists sometimes are like this, right? They do not reflect philosophically too deeply over what they're doing. So someone came up with this. They came up with this word-to-vec method in Google, and they're like, hey, it seems to work. And then if you look at early papers, people actually are like, hey, some analogies kind of correspond to addition or subtraction. So it seems like algebraic or operations on vectors correspond to semantic relations, and that's kind of hasty. Right, for this reason, because then you see a bunch of examples like that, and some people seem to be forgetting that what it was actually optimized for was not anything meaningful, but coherence. But then they also get inspired by those weird structuralist philosophers of language who go like, hey, everything is connected, like Dick Gently's kind of thing, It's all connected. Well, yes, but it doesn't mean that you can get the meaning back from coherence, right? So one reason why people pay attention, because there are clear-cut cases if you want to track it back. Another reason why people are not discouraged too quickly, because people doing computer science don't reflect too much on they get kind of fascinated with those known analogies and no examples where it seems to somehow capture something semantical. And what happens in the end is this, right?
So that was helpful, thank you. So if that's right, then this intervention, which I assume will be decisive for this particular, it'll be decisive object. Let's assume it's a decisive.
Sorry. One more thing, because you asked about the literature. So those who use this to study bias are quite convinced that this is a sign of bias.
Okay.
And they claim things like, hey, we can use it to see that when you apply this to literature over the last 100 years, it seems like things have gotten better in some respect, but not in another. They try to make some social kind of history.
Sure.
Sociological/historical claims. Right?
So I guess my question then, I assume all that is pretty much a wrecking ball for that view. But
I hope so.
The worry would be that they just move to another kind of arbitrary measure that doesn't have those specific problems.
Well, this is not an arbitrary measure.
No, sorry.
So our point is thinking of this in terms of measures is a bad idea to start with.
Yeah.
Because then you start chasing metrics instead of actually solving the problem.
Yeah.
And similar things happen in various contexts. Whenever you come up with a measure, then improving on that measure might not end up improving the original problem you wanted to solve, right? And that's one example.
So I guess I was wondering, in the upshot of this project, to prevent that kind of moving to the next measure that technically avoids those, the game that can be played by certain kinds of quantitatively minded computer scientists and so on, is whether there's a kind of an addendum to this that might help to point to maybe a more sophisticated philosophy of language that we might want to model. That would maybe point to a different set of tools than this basic kind of cartoonish structuralist view that you've been.
Okay, so So just like trying to present any statistical result by just giving the mean result or the mean difference is just going to hide or swipe all the uncertainty under the carpet, right?
Yeah.
Same goes here, right? Just like in standard context, Bayesians say, no, these are just summaries and they go only so far. Right? What you should do is you present the whole distribution and explain what the uncertainties are, and that's it. That's the best you can do, and that's what we do, right? We say, look, use the data that you have, perhaps improve the data to get better estimates, build proper statistical models, and then explain what the uncertainties are, and pay attention to the details. There is no single number, right? Because it really depends on, it also changes radically if you switch the exact neural networks that you look at, right? So it's not like these kind of shapes of biases are stable across various corpora that the networks was trained on. You can even use the same method and the same corpus, and you get slightly different results. So this is one of the problems, right? This is very unstable in a way. So the answer is no. Don't chase metrics. I mean, look at this level. Look at protected words. Look at this level of analysis, and present the uncertainties involved as honestly as you can.
Okay. So I guess I was pushing.
So the answer is no. Don't come up with another metric. Chasing metrics is stupid.
Yeah, I agree with that, and that's what I was worried about. I guess I was suggesting that. Sorry, I'll end my question now. I guess I was kind of prodding you to tell me whether you think the Bayesian analysis alone would be sufficient, or whether there's more like thicker kind of philosophy of language, like linguistics sort of theory that would be worth maybe a further project down the line when Alicja does her PhD or something, that would help to kind of push the debate that you're intervening in the right direction, rather than just like spinning the wheel of new metrics.
Interesting. So we spent some time trying to find some decently written philosophy of language papers that would provide some sensible theoretical underpinnings of the using cosine similarity as a proxy for kind of linguistics or meaning similarity or something like that, and we failed.
Yeah.
Interestingly, there are some bullshitty papers written in French. Pure coincidence, of course. But nothing really serious. And on those structuralist ideas. So this is probably the best shot that semantics, that the linguists have made, right? So
really.
When it comes to computational analysis of meaning, there are some other tools that also, but they all based on coherence, right? Yeah. And the idea that maybe the way words occur together is a guide to what they mean. It seems that they share the same problems. So and now the question is, okay, so what? Well, we have to process natural language somehow, and it still does a better job than what we had before. Okay. So maybe we should stop gunning for this resulting in a tool that actually captures semantic relations. But maybe that's not the name of the game. Maybe the name of the game is to have the system give us the right results when we need them. And then the question is, okay, yeah, this gives us weird results sometimes when you look at weird cases, but what we care about is that it works, but also it doesn't give us biased results. And in that sense, you can put the philosophical debate aside, because I think the project of finding sensible arguments to the effect of coherence can be a guide to meaning. That can just put aside, because it doesn't seem like a very optimistic prospect. But even that doesn't mean that you should not use cosine similarity or whatever. It just means you have to be extra careful. You have to remember that those relations are not semantic relations, in fact, and that some of those results, the weirdness of some of those results, is witness to them. That's the idea.
Yeah, that sounds great. Thank you. I have to run now.
Yeah, sure. Thanks.
Other questions?
I think Brandon is raising his hand.
Oh,
Brandon, yes.
Yeah, thanks. That was great. I really enjoyed that. I think my favorite part of it was when you did your own analysis of applying the methods to cases that you knew were not biased. I thought that was really useful. I think it would be useful maybe to go along with that to uh, give cases that clearly are biased and as a contrast and see how the methods do there. Um, and then I guess, so yeah, so my take on this, I mean, I'm very sympathetic to this. My take on what these folks are interested in is actually they're really just interested in prediction. If somebody utters some words in English, let's say, they want to be able to predict the next word they're going to say. That's really what they're, I mean, so maybe they talk about meaning, but when you talk to someone like Jan LeCun, I mean, he doesn't use the word meaning. He just talks about prediction.
Yeah.
So all they really care about is, can they predict the next word in a sequence of words by a user of the language? And that's very different than meaning. That's just predicting what the next word in a sequence will be. But given that that's their goal, maybe, I don't know, maybe it'd be worth looking at whether their methods are any good at that in comparison to alternative methods. Because if if the underlying statistical criticisms are true, it shouldn't really matter what the target of their analysis is, right? They should be getting the wrong answer no matter what the target is, because they're just doing something that's methodologically wrong. So anyway, so I think two things. It'd be good to look at cases where you think there is a bias, where there is a bias. Just make up a corpus where there is bias, and see how their methods do, and see how the other methods that you would prefer do. Um, and then also just see how they're doing on prediction. Like, are they really that good at prediction, or would other methods be actually even better at what they take their own task to be? The way I read it, anyway. But I need to study this more. It's really, really super interesting.
Yeah, cool, thanks. Right, so this is kind of part of my response to what Chad said, right? You can put aside those debates about whether cosine similarity captures semantics, right? You can think of it as a game where you try to predict the next word. Fine. And now the worry about bias is, hey, you might predict stereotypes to occur too often, and because they occur too often in the corpora that you train your network on. That's the whole worry can be formulated in terms of prediction. It's just when you read those papers, people overinterpret and overblow the adequacy, the kind of philosophical adequacy of cosine similarity sometimes. And even if you switch to thinking of this in terms of prediction, what happens is all the statistical criticisms apply. Yeah. Because now the question is, okay, would this network predict in a way that's systematically biased? Someone says, hey, let's plug in this score, and it seems yes. And what we're saying, well, let's think about it carefully and do proper Bayesian statistical analysis. There isn't sufficient ground for saying so. Right? So in that sense, most of what we say does not rely on this stronger reading of what word embeddings do, or are supposed to do. Even though this was the inspiration early on. And some people, especially those criticizing the framework, seem to be saying sometimes things like that, but we perhaps don't have to be committed to this. And as for finding cases where you have a clear cut of bias, we tried to find real data where you would get this result, but failed, right? So yes, in principle, we could come up with fake data sets, right, where there would be clear bias, and then we could see how the Bayesian method would do and how their method would do. Sure, but I think what would happen is the Bayesian method would give you the right results if the sample is big enough, and the usual old school scores would just go through the roof, right? Because they already do, right? In a sense, even for cases where there isn't bias. Did you raise your hand again?
Yeah, one follow-up. I mean, you could scrape data from like 4chan. I mean, if you want corpora that are biased, this is not hard. I mean,
No, but this is trained on Reddit, right? So this is pretty much as biased as it gets, and even then, right? The evidence is not strong enough. But this is partially because the word lists are kind of crazy. They should be longer and more principled. Then
okay,
with
but
papers, they're just like,
right,
hey, here is the word list.
right,
Without
right.
any,
But what I'm suggesting is, if so, there's the negative stuff. I think that's great, and okay, but towards a positive thing, you'd want there to be methods that could detect bias. So you'd want data sets that have bias. So you want there to be some consensus control data sets that everyone agrees are biased. See what I'm saying? You need to
yeah,
have those in order for the
yeah,
positive side of the
yeah.
story.
And for that, I don't think we have to scrape other corpora. I think for that we have to have better, larger, and more principled word lists.
Maybe both. Maybe both. I bet if you do 4chan, you get plenty of bias.
Okay, but I mean, so Reddit is also pretty bad. But yeah, good point, right? It would be nice to have a clear-cut case of real data where the bias actually arises and the method is capable of seeing it. Yeah. Are you there? Huh.
I have this frozen.
Okay.
Can't wait.
Did you get frozen? Did you hear what I said?
Yeah, no, I got it. That's great.
Okay.
Thanks. Appreciate it.
Just to follow up on what you said about like that metrics are it creates like something to chase and that they're not necessarily the way to go. It seems that like the idea of using a metric like this to quantify bias is that there's something intrinsic, like geometrically, about the relationship between like biased words, but it seems that like it's like inevitable that there would be co-occurrence between stereotypical words and like inevitable, like by definition, right? Because like if it's a stereotype, it means that
It's repeated more often.
right. So that same relationship would probably occur with different words that don't have like a harm associated with them, right? Like a non-protected group. So like, isn't it a separate like normative like intervention that's being made after the fact that would be required to like debias like one of these vectors, right? It's not like a mathematical relationship between the two, and like the it seems that the metrics are just they're insufficient because they're like sparse in dimensionality, right? Like you're taking a very like reduced kind of metric where like this is the kind of like complex function that like neural nets and these kinds of models are meant to do. So is it the case that like metrics in general are insufficient, or like you could use like a more complex one that uses the same kind of like deep learning technology or something to quantify this like relationship?
Interesting. Well, in principle, right, you could get rid of some of the difficulties, right? So for instance, at least you can avoid the problems with pre-averaging when you say, hey, let's pay attention to types of connections, right? Let's pay attention to which groups of protected words we have in mind. And then we can have honest Bayesian estimates of difference in distances or difference in similarities. That's something, right? But it's only as good as comparing the means goes statistically. So to some extent, yes, this would be more meaningful because it will be devoid of the statistical flaws. But still, the problem is, well, one problem is that all those methods rely on the way you select your word list. So in principle, right, if you come out, in principle, you can imagine this. Someone comes up with a more principled word list. Right? Turns out, hey, there is bias in your word model. So the engineers play around with vectors and they end up with something where you cannot no longer detect this bias. Does it mean that there is no bias that's learned from the corpora? Well, it might be that some other predicates that are not on the list, right? Because the way if you know what list you're tweaking for, right, you can optimize for hiding the bias or lowering the bias with respect to the word list. So the idea of hey, let's just have one single word list and let's just use it as a gold standard test to see if there's bias. That's doomed, right? Because people are smart, right? They're gonna figure out cheap ways out. course, then the other side might come up with a different word list to show that they haven't solved the problem. Now the question is how much progress can be made this way? Because another thing that happened that we did not discuss today is what happens when you look at the bias word embeddings. So some people try this, right? Some people try to optimize for removing this bias. Let's pretend it was there. Right? And in a sense, right, they did get some improvement, like hey, how you know, like these guys, right? They moved from what was this? They moved from 0.85 to 0.93, where 1 is supposedly the ideal. Okay. Some improvement, perhaps, right? But what happens, so we looked at those debiased embeddings, and it's not just that the things, the distances for the protected words and stereotypical predicates moved. Everything else gets shifted. If you just globally apply some projection or some transformational vectors, it's very hard to predict where it would lead you with respect to other words. And weird things happen. So, for instance, in some cases, human predicates, so it's supposed to be the bias, right? So, yes, the associated predicates and the different stereotypical predicates get moved away a bit, right? But then, what also happens is the human predicates like fly away and are less connected to the protected word than neutral words. Completely undesirable, right? So another problem is if you try to debias at the level of like, hey, let's do some algebraic stuff, their outcome is not easily predictable and it's very global, right? So it's very difficult to apply this to a particular class of vectors so that you end up with debiasing the right words without shifting the stuff around which you don't want to shift around.
I think just to follow up, though, I think that's what I mean. If you have a, let's say, a model that looks at restaurant reviews, there's a good chance that like fast food restaurants will be associated with certain words, and like Michelin star restaurants will be associated with other words, and like the same kind of geometrical relationship would exist between those vectors as would exist between these stereotype words, right? So
Yeah.
The problem is that
you get some asymmetry there. Yeah.
Right. The problem is that in the case of these protected groups that causes harm, and like that is the bias that you want to mitigate, and not necessarily the relationship. So like just applying like any geometric kind of intervention would like have that global shift that you're talking about. But it seems that like the kind of interventions that people are actually trying to get at would require like a more
Localized.
or like a complex like hyperplane that you're trying to map to that's not like geometrically obvious from the words, right?
Yeah, you're right. So, okay, so perhaps the biasing will not have much impact on the restaurant related vectors, right? Who knows? But you're right. It should be more careful and more localized, and doesn't seem like general geometric moves would help here in a way that would lead to equally dependable methods. So one of the issues is, hey, they also try to kind of test the biased embeddings like performance-wise, putting the bias aside. There's always some drop in performance, and that's it's a bit of a. Now that I describe it this way, it seems like there is a tension between statistical accuracy and fairness. I'm not sure if this is the case, right? It sort of depends on what's at stake in prediction. But that's a long story. That's a deeper debate. I don't want to get into it now. But yeah, global geometric solution probably won't work very well.
So do you think that large models could help with that, like large language models or other kinds of like more sophisticated things can help figure out that like relationship between like I'm sure also that like protected words are used differently in language, and those relationships can be gleaned somehow from like how they're used in bigger corpuses, right?
Well, not sure. I haven't seen much progress made on that. Because what you want to end up with is a tool that would also work well with whatever application Port embeddings have. And I don't think there's much on the market that compares. Perhaps again, I'm just guessing. Perhaps you should start more upstream. Perhaps the problem is, hey, you want a fair word embedding. Maybe don't train it in red corpora. So maybe upstream you should first be way more selective about what you're using to train the network. But then think about it, because networks like this require huge corpora, right? And that would require lots of annotation, and that's lots of time, lots of money. Might be unfeasible.
Well,
Yeah, thanks. So I have questions related to some of these things. I took the pre-averaging point to be like totally damning, so that was very compelling. And I wonder if this isn't, just another reason to doubt that, at least at the moment, we have any way of interpreting what's going on with the word embedding, where we're treating the spatial representation that we have out of the word embedding as like itself meaningful rather than just as a tool for prediction that we don't really understand why it works, but turns out it does. And so you were suggesting maybe one way of dealing with the bias we do see is by going upstream and just not mucking about with these things and pretending that the vectors and the relationships between them somehow encodes a meaningful, relationship. Yeah. But rather, look, it's this black box thing. We don't know why it works, but it does. I mean, as a matter of fact, it's using word embeddings. We've trained systems that are very reliable. And so rather than saying, okay, let's fix the fairness by messing with these internal systems we don't understand, we can either go upstream, like you were suggesting, just trying to debias the data antecedently, or we go downstream and say, look, here's a way where in some cases we might be better off using fairness metrics that we use to
Right, so you can have some downstream application kind of whose results are filtered by some fairness filters before they spit out crazy predictions, right?
So this is, obviously
and this is kind of what's happening, right?
Yeah, so kind of the way that the way that fairness criteria are being used now is a mess, but I mean, it's at least one better way here. We can say, look, to Brandon's point, it's like we see these things making predictions, and we want to know, are the actual predictions they're making bad? And we can see that sometimes. And so let's go look at that rather than trying to muck about with the vectors, which we don't understand.
Yeah.
So, I mean, I think that's like one potential upshot for what you guys are saying.
Yeah. So, and I think that the latter method is because this is what like Google and so on kind of seem to be doing, right? Because they seem to react to complaints and like, hey, it no longer happens that when you Google Latina teen, you get something that you probably don't,
And there's huge problems with that literature and the way people are doing those things. So not to push under the rug, but at the very least, it might be a better way of direction forward, and you guys can say, we are providing support for this idea that that's a better direction forward than trying to interpret these word embeddings.
Yeah, and one reason to think that this is something that they seem to be doing is like, it seems to be language dependent in the following sense. When you Google lawyer in English and you look at images, then around 40% images will be images that involve a female. If you do it in Polish, it's around 20. So they seem to be fixing things, but this depends on how many people they have working on a particular language. And they seem to be fixing them downstream.
Questions, comments? Let's thank Rafal.
And Alicja. Alicja, do you want to say something? Do you have any comments, Alicja? Oh, Alicja.
Yes, I just wanted to thank for all of the feedback because. Oh, sorry. Let me turn it off. It's just quite late at my part of the world, but I wanted to thank everyone for the feedback. I wrote down some ideas, and I think we'll be able to improve the research even more with some comments from Brandon and other people. So I'm grateful for your like inputs into our project. Thank you.
Okay, thanks for being here. So how do I, okay, so I stop share and I stop recording. See you guys. Oh, okay, Brandon left already, okay. So see you, Alicia.
Yeah, see you. Thank
Bye.
you.
Yes.